Hello students, it's Kailash. In this video session, you will be learning about the topic Spectral Series of Hydrogen. This topic comes in lesson 9 Atomic and Nuclear Physics of 12th standard. Well, I really thank everyone who have subscribed to my channel. If you haven't, please do subscribe to receive my updates. Okay, thank you. Shall we proceed to the topic? Well, students, the diagram what you see in the picture is the atomic structure of hydrogen atom. You know, atomic number of hydrogen is 1. It will contain 1 electron. The atom of hydrogen will contain 1 electron. And that electron spends most of its time under normal conditions in the first orbit. So the first orbit happens to be its ground state. Now, when energy is supplied to the electron of hydrogen atom, as per Bohr's postulate, whenever an electron absorbs energy, it has to jump from lower energy level to higher energy level. So when energy is supplied to the electron, it may undergo a number of upward transitions on absorbing that energy. And again, the orbit to which the electron is going to jump will depend upon the energy what we supply. See, I'm supplying a photon. The electron is absorbing that energy. And if the energy of the photon that is being supplied equals to the energy difference between the first orbit and the second orbit, the electron will jump to the second orbit right from the first. On the other hand, if the energy of the photon what we have supplied equals the energy difference between the third orbit and the first orbit, then the electron will jump to the third right from the first orbit. If the energy of the photon what we have supplied equals to the energy difference between the fourth orbit and the first orbit, then the electron will jump to the fourth orbit from the first. On the other hand, if the energy of the photon supplied equals the energy difference between the fifth orbit and the first orbit, then the electron may undergo the upward transition right from the first orbit to the fifth orbit. So upward transition here refers to jumping of electron from lower energy level to higher energy level. So like this, there are n number of upward transitions possible because there are infinite number of orbits in any atom. Okay. Now let us consider a different case. Now here you can see an electron in the higher energy level. Say here in our diagram, it's in the fifth orbit. An excited electron can also undergo a number of downward transitions, emitting photons or spectral lines. Photons otherwise called spectral lines, whose energy will be equal to the difference in the energies of the orbits between which the electron transition takes place. So if you consider an excited electron in the fifth orbit, it may jump to the first orbit. So during this downward transition, it is going to emit a photon. You can see a photon that is being emitted. You otherwise call it as a spectral line. The energy of the photon emitted will be equal to the energy difference between the two orbits between which the electron is undergoing downward transition. Here it is between fifth orbit and the first orbit. Therefore, the energy of the photon has to be E5 minus E1, where E5 is the energy of the fifth orbit and E1 is the energy of the first orbit. The electron may also jump from the fourth orbit to the first orbit. The photon or spectral line thus emitted will have energy equals to E4 minus E1. If the electron, on the other hand, jumps from the third orbit to the first orbit, the energy of the photon, what it delivers or what it gives up, will be equal to E3 minus E1. Now, the electron is jumping from the second orbit to the first orbit. Again, it is emitting a photon. The energy of the photon will be equal to E2 minus E1. So like this, there are n number of transitions possible, downward transitions in fact possible. Now during each and every downward transition, you will be getting a photon. Now bunch of all these photons when passed through a spectrometer will form hydrogen spectrum. Okay. Now again, before proceeding into hydrogen spectrum, you should know a beautiful term. You should be aware of a beautiful term, wave number, denoted by the letter nu bar. Just Write the symbol for the frequency nu and put a bar above it. So wave number. Now, what is this wave number? Wave number is defined as the number of waves present in 1 meter distance of a medium. So the wave travels through a medium. In 1 meter distance of the medium, how many waveforms are present? So that number is referred to as wave number. And you can't find this definition in your textbook. So please, you can make a note of it. Now, mathematically, wave number is expressed as reciprocal of wavelength. Now, we can also write this as a definition. So, wave number is defined as reciprocal of wavelength. So, nu bar equals to 1 by lambda. You know, the SI unit of wavelength is meter. So, meter. If I take meter to the numerator, it becomes meter to the power minus 1. Thus, the unit of wave number is meter to the power minus 1. Fine. Now we have one more beautiful definition for wave number in accordance to Bohr's postulate. So as per Bohr's postulate, let us consider an electron jumping from a higher energy level of principal quantum number m to a lower energy level of principal quantum number n. So when an electron jumps from higher energy level to lower energy level, it has to emit a spectral line, isn't it? Now the wave number of that spectral line is given by the formula nu bar equals r into 1 by n square minus 1 by m square, which in turn is equal to 1 by lambda, because nu bar is basically reciprocal of wavelength. So what is this term r in the expression? The term r in the expression is a constant called Rydberg's constant, whose value is 1.09737 into 10 to the power 7 meter to the power minus 1. And if you look at the formula very carefully, n refers to principal quantum number of lower energy level and m refers to principal quantum number of higher energy level. For instance, let us assume an electron is jumping from 7th orbit to the 3rd orbit. Among these two, the one with the lower principal quantum number, that is 3, is the lower value of principal quantum number. So I'll be taking n as 3. And the higher value of principal quantum number 7 will be taken as m. So among the two given principal quantum numbers, the one with the smaller value should be taken as n, and the one with the larger value should be taken as m. You have to be very careful in this aspect. Now, spectral series of hydrogen atoms. So as I told you, when electron undergoes downward transition, it emits a photon. Since in a hydrogen atom or in any atom, there are infinite number of orbits, there are n number of downward transitions possible. So during each and every downward transition, a spectral line or a photon is emitted. Thus, we'll have a bunch of photons, which gives rise to spectrum of hydrogen spectrum. Now, the hydrogen spectrum, in fact, is divided into 5 groups or 5 series. In each series, the wavelength of the spectral line or radiation approaches a limiting value called series limit. Now, what is the series limit? Series limit is the wavelength of the last spectral line that is being emitted. And we shall discuss about series limit in detail in the consequent slides. Now, what are the 5 different series of hydrogen spectrum? Number 1, Lyman series. Number 2, Balma series. Number 3, Passion series. Number 4, Bracket series. And number 5, Fun series. So these are the 5 different series of spectrum of hydrogen. Now we shall see one by one, right from the next slide. The first, we shall see what is Lyman series. When an electron jumps from any of the excited state to the first orbit, then the group of spectral lines emitted form Lyman series. So for Lyman series to be formed, the electron has to jump from any of the excited state to the first orbit. You can see the animation. You can see an electron is jumping from the second orbit to the first, third to the first, fourth to the first, fifth to the first, sixth to the first, and so on. During each and every downward transition, you would have observed photons being emitted. Now, bunch of all these photons or spectral lines put together gives rise to Lyman series. We know that mu bar equals to R into 1 by n square minus 1 by m square, which in turn is equal to 1 by lambda. Now, what is the principal quantum number of the lower energy level involved in Lyman series? Its n is equal to 1. You can see the electron is jumping to the first orbit. So I'll be taking n as 1. And what are the principal quantum numbers of the excited states from where the electrons are jumping to the first orbit? The excited states are second orbit, third orbit, fourth orbit, fifth orbit, and sixth orbit, and so on. So all these are all excited states, principal quantum numbers of the excited states from where the electron jumps to the first orbit. So the principal quantum numbers of all these excited states can be taken as m. So in Lyman series, the principal quantum number of the lower energy level is 1. It's same for all these transitions, whereas the principal quantum number of the excited states, the higher energy levels are 2, 3, 4, etc. up to infinity. So on substituting the value of n in this expression, you will end up with wave number nu bar equals R into, instead of n, I'm going to take 1. So 1 square is 1. So 1 by 1 is 1. So I get R into 1 minus 1 by m square. I'm not going to substitute any value for m because m can take any values right from 2 to infinity. That is equal to 1 by lambda in turn. Now, Lyman series lies in UV region, which means the photons emitted during these transitions shown in the diagram are basically ultraviolet radiations. So Lyman series lies in UV region. Now, what is that series limit? Now, what is series limit as far as Lyman series is concerned? Series limit refers to the spectral line that is emitted during the last transition. Now, what is the last possible transition in Lyman series? Infinite orbit to the first orbit. So if I consider an electron jumping from the infinite orbit to the first orbit, and this happens to be the last and final transition, you can see, you could have seen a photon that is being emitted. So that spectral line will possess largest energy, highest frequency, and hence smallest wavelength. So that particular spectral line is called series limit. So as far as Lyman series is concerned, the series limit refers to wavelength of that photon which is emitted when the electron jumps from infinite orbit to the first orbit. Is it clear? Right. Now we'll go into the next one. Balma series. When an electron jumps from any of the excited state to the second orbit, then the group of spectral lines emitted will form Balma series. So here the transition has to be from, the downward transitions in fact has to be from any of the excited states to the second orbit. So the electron is jumping from third orbit to the second, fourth to second, fifth to second, and sixth to second, and so on. So during all these transitions, photons are emitted. Now, a bunch of all these spectral lines or photons will form Balma series. You know, wave number equals to R into 1 by n square minus 1 by m square, which is equal to 1 by lambda. Now, the principal quantum number of the lower energy level to which the electron jumps is 2. In all these transitions, you can see the principal quantum number of the lower energy level is 2. So n is equal to 2. And what are the principal quantum numbers of the higher energy levels from where the electrons jump to the second orbit? 3, 4, 5, and 6. So I'm going to take all these principal quantum numbers of the excited states as m. So in this case, n is equal to 2 and m equals to 3, 4, 5, etc. up to infinity. On substituting the fixed value, that is n equals to 2 in this expression, retaining m as such because m has multiple values from 3 to infinity, I will end up with nu bar equals R into 1 by 4. 2 square is 4. So 1 by 4 minus 1 by m square, which in turn is equal to 1 by lambda. Now, Balma series lies in visible region, which means the photons emitted during these transitions will be light radiations. Now let us see what is a series limit in Balma series. Series limit refers to the final transition. So the last possible transition in Balma series is to be from infinite orbit to the second orbit. The photon emitted in such a transition will be having the highest energy and hence highest frequency and hence smallest wavelength. The energy of a photon is given by E equals to h nu. And you can see the frequency of the photon emitted or spectral line emitted depends upon the energy of the photon. And the final transition, when the electron jumps from the infinite orbit to the second or infinite orbit to the first, as in the case of Lyman series, will possess the largest energy, so maximum energy. Since the energy of the final transition is maximum, frequency of that particular spectral line will be maximum. Frequency and wavelength vary inversely to one another. If the frequency is maximum, and then the wavelength of that spectral line will be minimum. So the minimum wavelength of spectral line in each and every series of hydrogen spectrum gives rise to series limit. So this happens to be the series limit. Now, we shall go into the next one, Paschen series. When an electron jumps from any of the excited state to the third orbit. So for Lyman series, the electron has to jump to the first from any of the excited state. For Balma series, the electron has to jump from any of the excited state to the second orbit. And as far as Paschen series is concerned, the electron has to jump from any of the excited state to the third orbit. Then the group of spectral lines emitted form Paschen series. The electron may jump from fourth to third, fifth to third, sixth to third, seventh to third, and so on. The photons thus emitted will give rise to Paschen series. Wave number nu bar equals to R into 1 by n square minus 1 by m square, which in turn is equal to 1 by lambda. Here, the principal quantum number of the lower energy level to which the electron jumps to is n is equal to 3. So I'll be taking n value in this expression as 3. And for the principal quantum numbers of the excited states from where the electron jumps to the third orbit are 4, 5, 6, and 7, and so on. Thus, the value of m will have multiples. The value of m will be in multiples, that is 4, 5, 6, 7, etc. up to infinity. Thus, in this case, n is equal to 3 and m is equal to 4, 5, 6, etc. up to infinity. Now, nu bar equals r into, instead of n, let me substitute 3. So I end up with r into 1 by 9 minus 1 by m square. I'm retaining m as such because m has multiple values, right from 4 to infinity, which in turn is equal to 1 by lambda. Paschen series lies in infrared region, which means the spectral lines emitted during these downward transitions are basically infrared radiations, heat radiations. Now let us talk about the series limit in Paschen series. The last possible transition is from infinite orbit to the third orbit. So when an electron jumps from infinite orbit to the third orbit, it gives rise to series limit in Paschen series. And that particular spectral line emitted will have the smallest wavelength and hence largest frequency and hence largest energy. We'll go into the next one. Bracket series. Whenever an electron jumps from any of the excited state to the fourth orbit, then the group of spectral lines emitted from bracket series. The electron may jump from fifth orbit to the fourth, sixth orbit to the fourth, seventh orbit to the fourth, and so on. So here the principal quantum number of the lower energy level to which the electron jumps to is 4, and that of the higher energy levels are 5, 6, 7 up to infinity. So, nu bar equals to r into 1 by n square minus 1 by m square, which is equal to 1 by lambda. So n refers to principal quantum number, the lower value of principal quantum number, and m refers to the value of the higher value of principal quantum number. So here n is equal to 4 and m is equal to 5, 6, 7, 8, etc. Substituting the value of n in the expression, I get nu bar equals to r into 1 by 4 square, that is nothing but 16, minus 1 by m square, which is equal to 1 by lambda. bracket series lies in IR region. So the radiations which are emitted during these transitions too will be infrared radiations, but with a longer wavelength when compared to the earlier case. So the infrared radiations, what we get in Passion series will have smaller wavelength than the infrared radiations what we get during bracket series. Okay, so you call the earlier one as near infrared rays, and these infrared radiations what we get in bracket series can be called as mid infrared rays. And lastly, series limit. So in bracket series, to get the series limit, the electron has to jump from the infinite orbit to the fourth orbit. So the energy of that particular spectral line will be highest. Hence, the frequency of that spectral line is going to be the highest, and hence the wavelength is going to be the smallest. Now comes fun series. Whenever an electron jumps from any of the excited state to the fifth orbit, then the group of spectral lines emitted will form fun series. So the electron has to jump from any of the excited state to the fifth orbit. Can jump from 6 to 5, 7 to 5, 8 to 5, and so on. Now the group of spectral lines obtained will give rise to fun series. Again, nu bar equals to R into 1 by n square minus 1 by m square, which is equal to 1 by lambda. So here the principal quantum number of the lower energy level to which the electron jumps to is 5. And the excited states from where the electron jumps have principal quantum number 6, 7, 8, etc. So they are taken as n. Substituting the value of n, I end up with nu bar equals to R into 1 by 25 minus 1 by m square. That is equal to 1 by lambda. So here again, the fun series lies in IR region. That is, the radiations emitted during these transitions will still again be infrared rays, but of largest wavelength. So I'm going to call this as far infrared rays. Okay. Now, what about the series limit here? The electron has to jump from infinite orbit to the fifth orbit. So that particular spectral line will possess the smallest wavelength, and hence it forms a series limit in fun series. Now, lastly, you no need to draw the diagram individually for each and every series. You can draw such a consolidated diagram indicating all the series. Okay, so you can see Lyman series, Balma series, Passion, bracket, and fun series. So that's all about spectrum of hydrogen. I hope you would have understood. Thank you then. Meet you in the next video session. Until then, bye.